Good morning. Welcome to our session. I'm Yuan Chen from NVIDIA. Okay, let's echo from another room. I'm working with the NVIDIA DGX Cloud to build Kubernetes optimized AI infrastructure platform and for AI and GPU workload.
Hello, I'm Chen, a senior research scientist from IBM Research. I've been a very active contributor to Kubernetes and 6 Kubernetes, including the auto-scaling scheduling community, and now I'm contributing to the working group of serving as well, like this benchmarking tool.
Okay, so in today's session, we are going to walk through how to run model inference benchmarking, use the Triton Inference Server and FM performance tools. We will also cover how to run the GPU-intensive workload. In this talk, we will also cover some of the monitoring tools like the NVIDIA SMI and another tool called GPUStressTest. We will briefly and give an overview of other benchmark tools. Hopefully, and you will find this session helpful. Okay, let me start it. And so firstly, the Triton Inference Server is very popular and inference server, and it's open source tool, can run and a bunch of different models, and from like the typical and all these and popular models, and you can use it. It supports x86 and ARM. Also provide some client library and tools, including running on the edge and mobile devices. Also recently, NVIDIA announced an advanced version called Dynamo. It extends and optimizes the Triton with advanced features for improved scalability and performance. So in order to set up a Triton inference, so there are 3 key steps. The firstly, you need to create a model repository and populate with all kinds of different models. I will cover next some details how to do that. Then the secondly is deploy the Triton server instance itself. Also, Triton provide there are some client or workload generation tool and performance collection tool called Performance Analyzer, can collect, send a request, and collect all this performance data. So I will go through each of them one by one. So for model and deployment, and Triton support and all different models from PyTorch and to like the standard ONNX models and a lot of VLLM. So some example models like Llama and Falcon and other things. So if you look at the structure of the model repository, basically, and you can populate and deploy and all different models. So each model is a subdirectory, you name and the models. Under each model, there are configuration file. Also, you can have multiple versions for each type of models. So for example, just 1, 2, 3, name it. So on the right side, here is the examples. For example, you have text detection model, version 1, right? You have another one is text recognition, and yeah. Under this directory is the real model file, and yeah, they are the Triton supports, like I mentioned, all different and a variety and type or format of the models. So this is you populate it and the models. So a lot of models and available online. You can just download it and yeah, store and in a storage or file system. So the second step is set up, configure the Triton server, and we have containerized the version. So the Triton server, right, and have some client API receive the request. It supports both the HTTP and the gRPC protocol. Then inside, there are flow, processed request, send back the response. So this is an example in the YAML file, and very simple. And the most important thing, right, is you set up the Triton server ports. It supports both the HTTP protocol, which port we're listening to, also the gRPC port. So then you specify most important thing is the model repository, right? You can mount from your local host on this simple example, but it can be anywhere, right, in the distributed system. Additionally, you set up a service, right, listening to the port and where you want to get and listen and receive the request. Like here, right, we have gRPC protocol port and as well as the HTTP one. So the third step, right, you have to generate some workload and send the workload. And a very nice tool is called a performance and analyzer. It can generate the request sent to the Triton and the inference server. It also supports TensorFlow and the Torch serve as well. So they're all different mode, and you can send the request and from the the specified concurrency level and the specified rate, or you can also the interval, right? How you want to send the request. Also, how you want to measure the performance. Here is some sample on the output, right? How many requests you send. Also the latency, different percentile, 50 percentile, 99 percentile, and detail, and also the different concurrency level. So there are tons of different configurations you can try, and check out the reference for how to use this and the performance and analyzer. Yeah, if you want to run a containerized and a client generation, this is very simple example file. You can see, and the most important thing you specify here is you want to send a gRPC or HTTP request, and also which model you want to send the request to, as you see and early. So for the Triton server, we can populate the Triton Inference Server with a bunch of models. Here specify this and ResDat 50 as the model, and also request here is very simple. Just specify I want to send a constant and request 200 and request per second. Okay, another thing I want to mention, yeah, recently as part of the performance analyzer, and there are new and workload generate called MLPerf. So it's a specific tool for measure and do the benchmark for the generative AI models. So it's still under active development, but please check it out if you're interested. It can provide a lot of the metrics and the data for the GenAI specific and workloads. Yeah, like the time to first token and the inter-latency between tokens, other thing. It's going to be very helpful, useful tools to understand the behavior of this and the GenAI and the model inference. So as part of the benchmark, we know, right, a monitoring tool and other things are important. So of course, if you are familiar with the GPU setup, the most useful, or you should consider to use NVIDIA SMI, NVIDIA System Management Interface, to collect the data, and it can show you, this is A100, which each node have 8 and GPU devices, right, like the GPU utilization, temperature, memory usage, or other thing. Another useful tools I used and from open source called GPUStressTest. I think it's a very useful tools, can show you real time, right? Each of the GPU devices temperature, GPU utilization, as well as the memory consumptions. So you can try it. So I also list some of the reference here. Okay, so use cases, actually we use this and Triton and the inference server. My colleague Kevin Cruz and I gave a presentation last KubeCon at KubeCon Salt Lake City, and we do a benchmark study, compare different GPU share strategy like time slicing and MPS multiprocess services, compare the trade-off and different sharing strategy for different workload. So if you're interested, check out, and we gain a lot of the insight by using this and the Triton benchmark and inference server. So okay, so next, let me see, hopefully I still have time. Okay, I will try to give a live demo, even I recorded, and I know live demo is risky, but I think it's probably more interesting. So let me see if I can make it work. So I hope, can you still hear me? No. Hello? Oh, okay. So now, and this is actually on my workstation. So like I mentioned, you need to populate a model first. So here I already populate a bunch of the models. And like I showed you earlier, and the model, and you can see each model, right? And yeah, there will be a model like the label and file, yeah, whatever, and yeah, you define it. Then under the model, and you have, I only for this one have a version 1, right? If you look at, that's the real model, right? It's quite big, and yeah, that's basically what you need. And we have a bunch of model already here. So now, and I deploy this model, right? And as I showed earlier, yeah, this is the YAML file, very straightforward, and there are already images provided, and in our NVIDIA and registry, and you specify the amount of the model and a bunch of metrics you want to collect it, and specify the port and the other thing, okay? Okay. As you see, it's running, okay? Let's see, and okay, that's the log of the server, Triton server. As you see here, a bunch of the model already populated, right? We have like 9 or different models. Also, it's true, right? It's listening to the different port for different requests. Okay, now let's see the client. And okay, the client was quite simple, this example 1, right? You just run also their containerized version. You just run the performance, and analyzer specify the port you want to send, also the model name, and I want to measure the 95% health, and use gRPC protocol. The request rate is 200, right? Okay, let's see. And okay, you can see both are running now, and if you use the NVIDIA SMI, you can see the utilization here, right? Both and are running, and also, yeah, that's the tool you can see, because the client sent the constant request, so the GPU utilization is 21, 22%. Yeah, I just run a very short period of time, it's done. Now, if you go back to look at the output in the client. Okay, you will see this and the detail of the, like this one, of course, the batch size 1, you can specify other thing. How many requests is greater than like 3,600 requests, or different percentile of the latency and the throughput or other thing. So this is just the basic set of the benchmark, and hopefully you find, yeah, it's quite straightforward. They're containerized version. You populate the model, you just start a Triton server. You can use this performance analyzer to generate a workload, collect the detail of the information. Okay, so now I will switch back and give it to Chen to present. Okay, the foundation model performance.
Hello. So today I'm bringing a project initially developed by IBM Research, and we actually open source it in the open source community, and later donated to the serving working group to consolidate like open source community effort. So as you already see, that Yuan showed the general workflow of the benchmarking process. You need to prepare the server deployment. You need to prepare the load testing job deployment. You need to collect the data, necessary data. So this framework is exactly help you to ease that process by providing you a programming interface in Python. And let's go through the details of it. So what is Fmperf, right? It's a Python-based benchmarking tooling library designed specifically for evaluating performance, efficiency, energy efficiency of large language model or Gen AI serving frameworks, such as the server, VLM server, or TGI server, which is the IBM forked version of TGI server. And then why we want to use Fmperf? Because it's kind of provide you a simple but very powerful Python API. So you can, so it allows you to deploy inference servers as Kubernetes deployment and services without the hassle to define all your YAML deployment, service YAMLs, etc. And then it gives you the simple Python interface to create different types of load testing, and within the Kubernetes or OpenShift environment. So why we target Kubernetes? So of course, this is KubeCon. Everybody is concerned about Kubernetes. But the initial objective for us is Kubernetes environment actually allow you to do consistent and reproducible performance benchmarking and testing across different types of servers, different types of load testers, and also different types of infrastructure. So this is the high-level architecture of Fmperf. Basically, you have a module called Fmperf library, which you can use in a simple Python script to configure what server you want to benchmark, what types of load tester you want, and then how long you want to run the experiment, right? And then behind the scene, it actually used the Kubernetes client library to allow you to deploy different server deployment, create corresponding services, mounted the necessary persistent volumes, and here we specifically, by default, it will mount the slash models for your model files and the slash request for different types of data traces you want to do the load testing. And then for the server deployment, right now we already support VLM and TJs, and we expect to support more like Triton and other servers, for example, as GLAN. So here is a list of initial contributors from IBM Research. I really want to thank to them. I'm one of the first adopter of this Fmperf library. It helps me a lot in terms of benchmarking performance across different hardware servers and different versions of the servers for optimizations. So key features of Fmperf, first it's automated deployment using simple Python code. I will show the example. And then it provides a simple load testers for different scenarios like homogeneous workload scenario, heterogeneous workload scenario, and also we have some models behind the scene based on our real production traces. So you have more realistic workload testing. And then right now it supports multiple inference servers, and we will expand the list in the future. And then we extract LLM-specific metrics, as Yuan already mentioned. The important thing, for example, time to first token, inter-token latencies, throughput, and then in addition, we actually collect the metrics from GPU as well using the tool Yuan mentioned. So we have some energy efficiency metrics available as well. And because you have a simple Python library, you can write a script, and then it can also help you. For example, you are developing and optimizing a server framework, and you can also use this library to write your own Python script to integrate with your CI/CD pipeline. So every version of optimization you did, you can kind of compare and automate the performance benchmarking for your servers. So I will then dive into how can we start using it. It's very, very simple. We just need to define 3 types of Python classes. The first one is cluster. Of course, it supports local and remote Kubernetes servers as long as your client laptop has access to the all connection to your clusters. You can define it using, for example, the load kube config in Kubernetes client to initialize the cluster class. And then the second one is workload spec. Workload spec allows you to define like what load testers you want to use. For example, here we use the default Fmperf load tester image, but you can change it to Triton client libraries or other types of load tester libraries. And it provides 3 types of workload specs, including homogeneous workload spec, which just defines the fixed input-output tokens for the stressing testing purposes. So it's more consistent and reproducible benchmarking use cases. And then you can define the heterogeneous workload spec that allows you to plug in different random distributions for your input-output tokens, for example. And then it's ideal for testing performance under some diverse request patterns. And then, again, realistic workload spec is something we contributed to the open source from Fmperf. It really learned the trace patterns from our production logs, and then we provide statistical modeling fitted to those production logs. So you see more realistic patterns. So the third one is model spec. Of course, you want to understand which model you want to benchmark, and then some configurations of the models, whether you want to enable, for example, the quantization, some different configurations in model compilations. And we specifically right now support TGS model spec and VRM model spec because they allow different input argument configurations for the servers. And of course, you can also define, for example, what GPUs you want to benchmark this server on, what is the CPU and memory allocations you want the deployment to be. So those are just three simple class definitions or declarations you want to have in your Python script. And then the only function you need to call is called run benchmark. So basically, you pass the cluster, model spec, workload spec into this function, and then you configure how many times you want to repeat the experiments, and then how many concurrent users you want to emulate or simulate in your benchmarking, and then how long you want to run the experiments about, and then all the Fmperf library will help you go through the workflow of deploying a model server, generated the workload, and runs evaluator pods to collect the data. And finally, you just need to check the data. So, and then for the results, we actually provide two types of results. One is the CSV summary of all your experiments in different reputations. What are the statistics of, for example, throughput, prefill latencies, inter-token latencies, end-to-end latencies, etc. And then if you want to get into the details, we also have the load tester pod will actually write some detailed information about the timestamp of each token, and then the inter-token latencies in a JSON file, so you can later review all those results. So, okay. So compared to popular benchmarks you may heard of, like MLPerf, Fmperf, the distinct capabilities Fmperf is providing is really Kubernetes integration. So Kubernetes environment allow you to do the repeated, reproducible results of benchmarking. And then, for example, MLPerf is more focused on giving you some accuracy and latency constraint, and then let different submitters to improve their optimizations to show which server has better performance. However, those are not necessarily easy to reproduce. And then Fmperf run load test again. The existing services, especially commercial services, so it doesn't give you the choice to deploy your own optimized server versions. And then Fmperf is really for yourself to compare, for example, different versions of your inference servers and different versions of your hardwares to actually give you an idea on whether you are improving your server performance or you got some regressions in your server performance. So there are also a lot of other open source benchmarking tools from different communities. We actually, in the working group of serving, we started all of those, and then we decided to consolidate the effort into a standard way to contribute. And then Fmperf, we actually donate Fmperf to this community, so we help other companies or other contributors to not repeat the same tooling process, like creating YAMLs for the deployment and jobs. And then, so the unique part is we focus on the code-first approach. So we provide code library to easily launch the benchmarking. And then we want this class to be extensible, so we can easily extend it to more types of servers, right? And then we focus on Kubernetes native integrations. So I will show a quick demo on how we can easily use Fmperf. So here we have some local folders mounted to the current cluster on the mount models and mount request. And then we first just check if the both volumes are properly mounted. And then here, I will show a simple like VM benchmarking script. So you can see all you need to do is to define the cluster spec, workload spec, initialize the cluster, right? Configure some security context, and then configure how long you want to run the experiment and just run benchmark. Those are all the things you need to do. Then we run it. You can see like in the kube control get pods monitoring, we already started creating the deployment of the VM server. And then, of course, it takes a while for the VM server to boot up. And when it's ready, it will continue checking your workload spec configurations and start another job. Right, here is the Fmperf generator. So this workload spec is using the native Fmperf load testers. And after configuring what data set you want to import into your load testers, we will launch a pod called evaluator. The evaluator is really just sending the request to the server and then summarizing the results. So we actually launched 2 experiments here. One is emulating one user keeps continuous sending requests. The other is 2 concurrent users sending requests. So here are the results of the summary. This is the CSV. And then you can configure a parameter called repetition. So you can conduct the same experiment multiple times with the same configuration. So you get very robust performance benchmarking results. And then here is a the detailed result JSON file that gives you each token's timestamp, decoding timestamp or prefilling timestamp, and how long it takes. So this is really a quick demo, and the demo video is available on YouTube as well. So as I mentioned, so we actually donate this. We actually donate this library to the Fmperf project. And right now, it supports the Python library. It supports the VLM model server and TGS model server. And then I will ignore all of those, as you may already heard it from the working group of serving talk yesterday. And in the future, because the serving is not just a server. If you think about it, it's an inference cluster. And we, in the open source, have a lot of orchestrators, inference cluster orchestrators like production stack, AI bricks, or even Dynamo, right? So in the future, we want to expand these benchmarking libraries to not only benchmarking the server performance, but also different use cases like long context, QA, summarization, agent. And then our focus will be expanded to not only the server performance optimizations, but what kind of routers performance we should have, and then whether we can better reuse the KV cache, etc. Okay, I will hand it back to Yuan.
Okay, hello. Thanks, Chen, and for giving. So Yeah, we're running out of time. I just quick mention, if you want to do some GPU and intensive workload benchmark, the GPU burn is a very useful tool. You can try it out. It's open source, also have the containerized version. Unfortunately, I don't think I have time to demo it, but very straightforward. You can specify how much memory and it will consume, also how long you want to run, right? Just try it. And you also can use the monitoring tool I mentioned earlier, like the NVIDIA SMI or GPUStressTest to collect all this information. We also use this benchmark to study the different GPU sharing strategy in our previous KubeCon. Please check it out. So I will skip the demo. So also there are other benchmarks and Chen already compare, and I'd like to highlight a few of them. Very comprehensive set of the ML benchmark for all the machine learning, HPC, and generative AI is called MLPerf benchmark. Also, recently, NVIDIA announced the DGX Cloud benchmarking service. Please check it out as well. So, okay, to summarize our talk, benchmarking is essential for understanding optimize the AI workload. So the key takeaway is there already a variety and a set of tools available and also benchmark and software. So you should try it. But moving forward, I think we need and probably provide the software tool can do all this more realistic end-to-end performance, right? It's not just about training or inferencing, and it's the end-to-end solutions, even data processing, post-processing, other thing. Another thing is not only the synthetic workload for what-if analysis, also can replay some real traces. That's important. Also, simulation, emulation are used for technicals, for deeper and insight. And finally, I also want to mention, DI is the new API to request allocate GPU, and you should take a look at it. And finally, I want to highlight the AI workload and not only about performance, reliability and failure recovery are very important. How to support that and evaluate this and the feature and will be critical features. Hopefully, the community can work together to improve it. Finally, all these tools you have seen so far, are publicly available, and definitely we should make it open source, and the community can use it and work together to enhance and develop the new features. So yeah, we list a bunch of the reference here, and you can take a look. So I will be at NVIDIA booth this afternoon. Yeah, also we're available and after the talk. So please come talk to us, and yeah, any question, comments, or feedback. Thank you very much.